Okay, good morning, everybody. So let's start today's seminar. So this is the last seminar of our group. So the speaker is Professor Seongchan Park from Yonsei University, and he's now visiting KIAS, as you will know. And he will going to talk about Festina-Lente Bound on Higgs vacuum structure and inflation. Please start.
Thank you very much. It's a great honor to give the last seminar of this year. Please enjoy my talk. So as Dong already mentioned, my talk title is FestinaLente Bound, and I'm going to discuss Higgs vacuum structure and also inflation. So this talk is based on my recent paper with Sungmook Lee, Dongyan Chang, Sangcheol Hyun, and also my colleague Min-seok So. Actually, Min-seok brought the idea of FestinaLente Bound to my group, and we started to discuss potential applications to actual particle physics, and we found that the FestinaLente Bound can be really useful to understand the Higgs vacuum structure and also inflation. Okay, so let me begin with this page showing you the meaning of FestinaLente. FestinaLente is a classical adage and oxymoron, meaning make haste slowly. Okay, and as this symbol shows, you may go fast, but with enough care. So you cannot really go faster than certain limit. Okay, this symbol has been used for many years in Europe from Middle Ages. And this word, the FestinaLente, was adopted as a motto, particularly by Emperor August. So he wanted to his army march fast, but with enough care. So the meaning is actually simple. So if tasks are rushed too quickly, then mistakes are made and good long-term results are not achieved. So these words can be used in several circumstances. For instance, this. You may talk to your students, FestinaLente, to push the project, okay? So FestinaLente Bound was suggested in recent two papers. So first paper is this paper by Montero, Riet, and Venken, and they analyzed effective field theory from the charged black hole evaporating in digital space. And after a while, they add one more author, Kumnum Bafa from Harvard, and they consider the FestinaLente Bound and its phenomenological implications. Okay, so from now on, I will tell you what is FestinaLente Bound and how I can use the FestinaLente Bound for actual particle physics situations. Okay, so this is from the first paper. So let me just read the part of the abstract. So in the swampland philosophy of constraining effective field theories from black hole mechanics, we study charged black hole evaporation in digital space. Okay, so this kind of work, this line of work, is now regarded as the program, the swampland program. So in the swampland program, people wanted to find the consistency conditions for effective theories in low energy from quantum gravity, full quantum gravity. Even though we do not really know the quantum gravity, we can guess what would be the consistent form of the quantum gravity, and we can try to learn the effective theory from those kind of particular quantum field theories, okay? So in this paper, they consider black hole mechanics, especially a charged black hole evaporation in digital background. Okay, as you can notice, This may be used for our universe because our universe is best described by lambda CDF, lambda CDM. Here, lambda is cosmological constant, and our universe itself is the zeta. Okay, and by considering this black hole dynamics, they found a lower bound on the mass of charged particles by demanding that large charged black holes evaporate back to the empty de Sitter space. Okay, so this is important message. So they just consider the black hole evaporation and found a bound on the mass of charged particles. So to have charged particles, what you need is unbroken U1 gauge theory, gauge symmetry in your theory. So you really need to have unbroken U1 and charged particles. Also, you apply the same bound, you really have to have the digital background, asymptotic digital background. So you just consider the black hole in digital space and start to allow the evaporation of the black hole through the quantum effects. For example, Hawking radiation or Schrödinger pair production. Okay, because you also have unbroken U1 charge, you have a charged black hole solution, so you allow the Schrödinger pair production as the function of masses and charges of elementary particles in the theory. Okay, and after all, the charged black holes in digital should make haste to evaporate, but they should not rush it. So that's how they made the name of the bound, the Festina-Lente. Okay. So this is the second paper with the Kumlum, and in here they basically want to apply the FestinaLente bound to the actual physical situation, and they discuss phenomenological implications of FestinaLente bound. Okay, so they, for instance, most importantly, they consider the Higgs potential, and they find that, including explanation of why the Higgs potential cannot have a local minimum at the origin, thus explaining why the electroweak force must be broken. Okay, I will come back to this point later. So to discuss FestinaLente bound, I first want to introduce you charged black hole solution in digital space. Here I set the sign of space-time metric minus and 3 pluses. And this black hole solution is called Reissner-Nordstrom digital black holes. That has been known for many years. So you can just trust this solution. This is a mathematical solution from the asymptotic digital background. Okay, so to set the asymptotically digital space, we can parameterize cosmological constant 3 over the digital horizon, size of the digital horizon squared, and that is positive in our universe. And also to have charged black hole solution, we need to have a gauged U1. This should be unbroken. That's how we can allow asymptotic U1. So you can add up the U1 charges for the black holes. So this is the action for the gravity and the U1 gauge boson. So this first term is famous Einstein term, and second term is from this cosmological constant, and third term is from the gauge, the U1. Okay, you just accept this as a theory for our universe itself, right? We do have unbroken U1 ENM, and we do have positive cosmological constant. We do have gravity. So this is the simple, probably the simplest version to describe the bosonic part of the relevant bosonic part of our universe. Okay. So having this and demanding the spherical symmetry, you can find the Rajnev-Nordstrom-de Sitter solution, that is black hole solution. So this U and U are the same function, Leb's function, and this Leb's function is given by this form. So 1 minus 2gm over r. So you can easily notice this 1 minus 2gm over r is for the Schwarzschild solution, right? And by turning on the U1 charge, you need to add this electric part. So this Q is electric charge. And finally, to consider the asymptotic de Sitter space, you need to add up this R square over L square term. Here, this solution is applicable for the domain of R from 0 to L de Sitter. So you can cover the whole universe. So here, L de Sitter can be regarded as the de Sitter horizon of our universe. So having this Leb's function, you can find the event horizon by solving this equation. The Leb's function goes to 0. When Leb's function goes to 0, this term diverges, then that's how you can find the event horizon. And you can easily notice you can recover the Schwarzschild solution by setting up the de Sitter horizon to be infinity and charge to be 0. Okay, so uncharged asymptotically flat space can be recovered from this solution. Okay, so this is the solution. You can find this by using whatever tools you can use. Okay. So now let's. Okay.
I have one question about
Yes.
the slide. So when you take this space LD is going to infinity, the lambda CC goes to 0.
Yes.
Right. I'm wondering if this lambda going to 0 limit is smoothly matched to the lambda equal to 0 or not?
Yeah, still this theory doesn't involve any massive graviton mode. So you can smoothly connect to the flat space, at least for this black hole solution.
Okay.
Thank you. So now let's try to solve this equation, U equals 0, to find the event horizon. To analyze this equation, I set the unit of the length by this. So the horizon of the universe is set to be 1. And I introduce dimensionless charge Q, which is defined by this form. Okay, for the given ds, and for the given G Newton, and for the given strength of the U1 interaction, you can set dimensionless charge like this. And also I set a dimensionless mass for the black hole like this. So G to the MR over L square. Okay, so by setting this, you can find the dimensionless equation. Okay, and it is useful to multiply minus R squared to U to set the equation simpler. So by setting this, you find the same equation, U equals 0 becomes this. So R to the 4 minus R squared plus 2mR minus Q squared becomes 0. Okay, this can be solvable because this is just quartic equation. And this delta is the discriminant of this quartic equation, and this equation has two solutions, two real solutions when this discriminant is larger than 0. Okay, and discriminant for this quartic equation is found to be this m squared minus q squared minus 27m to the 4, 36m squared q squared minus 8 times q squared q to the 4 minus 16 q to the 6. Okay, and by setting up delta equals 0, you can find the physical domain in q and m space. Okay, how can I get this? It's easy to use Mathematica. So by just using this discriminant, you can find the discriminant of your equation. Okay, so by plugging in the same equation in here, the Mathematica works for you and find this discriminant equation. And indeed, this delta is discriminant over 16. Okay, you can find this is exactly same as this. Okay, now you can even solve delta equals 0 by using this contour plot. That's pretty easy to use the Mathematica. Okay, so by setting up d equals 0, your Mathematica gives you this plot, this nice plot within a second. Okay, this is M, this is Q. So in Q and M, M and Q plane, you can find the shape of this physical domain. Okay, within this domain, this plot is the physical domain. The outside of this curve is unphysical. Okay.
One more question about
Yes, please.
this previous. Yeah. So what do you mean by solvable? So because
solvable means solvable
quantity,
means you can find the real solutions.
but how many real solutions are you talking about?
Actually, you can find the two real solutions by turning on Q and L.
Yeah, if Q is real, minus Q square means that this quartic polynomial always hit the real axis at least twice, right?
Yeah, so that
I
can
don't understand why you need this discriminant.
Well, this discriminant tells you how many real solutions you have. So when this condition is satisfied, you can find two real solutions. That's it. Unless you have real solutions.
In general, you can have 4, right?
Yeah, in general, you have 4 solutions in complex domain. By setting these conditions, you can find the real solutions. Just like the quadratic equation, when your discriminant of quadratic equation is larger than 0, you can find real solutions.
Well, I may be confused myself, but this quartic equation here, r to the 4th coefficient is positive, and you have a minus q square when r equal to 0. The function is minus q square, which is negative, right?
Oh, sorry. So when q equals 0, you have this equation, yeah.
So if q is not 0, then you always hit 2. At least you will have always 2 real solutions, right?
Oh, well, that depends on this condition, actually.
Okay, I can answer you later. I mean,
Okay.
maybe I'm making stupid mistakes here.
Okay, yeah. So anyway, yeah, this is a fairly simple mathematical analysis about this quartic equation, and this condition gives you 2 real solutions. That's what I want to say here. Okay.
Sorry, I'm also confusing. So why we have 2 solutions? I mean, one is the inner
it could be
the
one
cosmological horizon, right?
Yeah,
And one is
could be 2. Yeah, that's right.
Not 3. I mean, the charge black hole has.
Yeah, even you can allow 3 solutions, 4 solutions, right? Yeah, this is quartic equation. So in general, you can have 4 solutions, right?
Yeah.
So here, demanding the reality of your solutions, you really find you want to have the real horizons. That's what I want to say.
No, I mean, the charge black hole has 2 horizons, which is inner horizon and outer horizon, and we also have the cosmological horizon, right?
Yeah, they are separate here. So cosmological horizon is said to be 1.
Okay. So each solution is the inner horizon and outer horizon of the black hole.
That's right. That's exactly what I meant.
There is cosmological horizon at r equals 1.
That is right.
Okay, thank you.
Yeah, so here the size of horizon is measured by this unit, the horizon. Okay, so R is less than 1 in general by setting up this. Okay, let me go on.
Okay, then maybe the reason you need the discriminant. Now I can roughly understand. Okay.
Okay,
Yeah.
okay, thank you.
R should be less than 1.
Yeah, right, that's right. That's right, yeah. So let me look into the phase diagram more carefully. As you can notice, the shape of this phase diagram is like a shark's fin. So this phase diagram is sometimes called shark fin diagram. So outside of shark fin is unphysical, super extremal, and extremal, there are several different branches. So this branch is called extremal branch, where the topology is given like this, ADS2 times S2. And this branch is called charged Nari branch, where the size of horizon, outer horizon is same as the digital horizon. And this branch is called Schwarzschild digital branch. And here charge is already set to be 0, but you still have the Schwarzschild black hole, okay? And this line is called loop 1 line, where Q equals set to be 1, M. And if you have a particle, the black hole, which has exactly same charge and the mass, then you can follow this line, okay? Okay, so now let's consider the evolution of the black hole. So by setting mass and charge, you can find some place in this plane. For instance, you can find your black hole solution somewhere here, okay? Then you can read your mass here, and you can read your charge here, okay? You cannot allow the black hole solution outside of the phase diagram here, okay? So now let's consider the evaporation of the black hole. So let's start from this point. So again, you define your initial black hole having mass here and charge here. Okay. By allowing some mechanism, radiating particle, Hawking radiation or Schwinger pair production, your black hole lose charge and the mass along this line. So by having following up this line, you end up with this point, and you see your black hole is massive or chargeless. Then after then, your black hole evolves along this line, and you just lose the mass, not the charge. Charge is already radiated out, so your black hole is already neutral.
So, sorry, how do you lose charge? Because
by radiating charged particle.
But we don't have charged particles in the model. There's only a U1 gauge boson.
Oh, I'm sorry, I didn't include the fermionic sector here.
Okay.
In this in the action, this fermionic sector doesn't change your black hole solution.
Okay.
You
so
still,
you have
you
some
still allow
fermions charged under the U1, and you lose charge by basically pair producing the charged particles, and one gets recaptured and the other one gets sped out of the black hole. Or
that's right. Yeah.
I see. Okay. Thanks.
So you can allow charged particles on top of this black hole background. Then you can consider the Hawking radiation and Schwinger pair production by emitting those charged particles.
I see. And they don't modify the solution.
That's right.
The black hole solution, because they don't, but they contribute to the energy density, no?
Energy density, right? But the black hole solution itself is the vacuum solution, so you don't need those particles.
I see. I see. Thanks.
Okay, good. So by emitting charged particle, you may follow this line first, then follow this line. Okay, so you end up with the vacuum solution. Okay. Now I want to consider another case, another extreme case where I have a particle which is massless, but still has a charge, positive or negative charge. positive charge. Okay, so let me begin with this point again. Then by emitting massless, almost massless particle, which it doesn't have any size of a kinetic energy, you can find the emission of energy along this line, almost vertical line. It cannot really vertical line, but it is pretty close to the vertical line. Just imagine your charged particle doesn't have any kinetic energy, but still pops out of the black hole. Okay, so black hole lose then the charge, but not the energy. So in that case, you follow A line first, then you follow the B line and end up with the vacuum solution. Okay, yeah, this looks fine, right? However, if you consider the same process from, for instance, tip of this phase diagram, you immediately notice this cannot be the case, because when you lose the charge along this line, you just go out of the physical domain, and your black hole solution becomes unphysical. So you can find the naked singularity in the universe, right? You start from the largest possible black hole and lose your charge, then you only leave the singularity inside the universe, and so you really have to have a singularity. So you cannot tell this is physical process. Okay. So basically, what the authors of the Festina-Lente Bound found that there should be a certain limit of the mass for the charged particle. You shouldn't allow this process. Okay, so they just analyze the geometry more carefully and try to get the universal bound for the charged particle. Okay, so they so you want to allow all possible charged particle spectrum in your theory, but that, for instance, if you allow charged massless particle, your theory is inconsistent at the fundamental level. Okay. So basically, you want to allow this kind of process, only this kind of process, and not others. Okay. So this looks pretty smooth and physical, but this doesn't. Okay. So what's the bound? This is the bound. You can just analyze the geometry, and you can easily find this bound by yourself. Okay. Here, m is mass of charged particle on the unbroken U1. And this alpha is the fine structure constant of your U1 theory. And this Q is charge of your theory in the fundamental unit. And V is the scalar potential energy or cosmological constant of digital background. Okay. So this bound tells you all charged particles should be heavier than this fundamental critical limit given by the digital vacuum energy. Okay. Unless if you allow one particle which is lighter than this limit, you already broke the physical condition, okay, consistency condition of your charged black hole evolution. Okay.
So if in this equation, if V is a cosmological constant, then the meaning is clear. But if what if the potential is a function of some scalar fields?
Yeah, that will be the topic of my later part.
Okay.
But I can simply tell you, if V is slowly moving, very slow, then you can still accept quasi-digital solution as the background, and you can still find the quasi-digital charged black hole solution in there, and you can still find this kind of the bound. Okay. So in that case, V can be the height of the total the potential. Okay, let me move on. So now let's consider the applicability of the FestinaLente bound. Okay, so first of all, as by construction, if we are staying in the digital vacuum at the minimum of the potential, then you can apply the FestinaLente bound. But still, physically, we can allow the FestinaLente bound for a pseudo-digital background when the slow roll potential satisfying a short lifetime of the black hole. So you just compare the lifetime of the black hole and lifetime of your digital pseudo-digital background. And if the lifetime of pseudo-digital background is much longer than your black hole, you can still apply the same FestinaLente bound. Okay, and you can quantify this condition for the potential. Then we can define the potential slow roll parameter like this. This is just used in many inflation models. Anyway, we can use the same slow roll parameter. And if the form of the potential is given by this, here the V is the function of phi. Phi is the potential scalar field, and given by phi to the 4 and the running coupling, constant running coupling. Then by taking the derivative of the potential, you can find the slow roll parameter is given by this form. And this can be easily read like this. And this is beta function of your theory, scalar theory. And this lambda is the effective potential. And when this whole thing is much smaller than 1, you can apply the same FestinaLente bound. For instance, for Nari black hole, actually G times root V being the electric field, and we request this slow roll condition. So you can still read the mass of a black hole should be within the range where Q times E Nari gives you a very small value for this combination, exponential value. Okay, so the point is this: you can apply the FestinaLente bound for the stable digital background, and you can still apply the same FestinaLente bound for pseudo slow rolling potential. Okay, that's what I want to say here. Now let's try to consider phenomenological implications of FestinaLente bound. This is the simplest application of FestinaLente bound. So let's consider our standard model. Then the lightest charged particle is electron. Okay, we have unbroken U1 EM, and the mass of electron is 0.5 mega electron volt, and Q is 1. Okay, and we want to compare this mass and cosmological constant. At the current universe, we learned from many experiments, many observations, that cosmological constant is set to the vacuum energy, and the cosmological constant to be measured by this number, 2.8 times 10 to the minus 122 m Planck squared. Okay, for instance, this value was quoted by Planck. Okay, then you can easily notice FestinaLente bound is satisfied because this lambda is so small. Okay, this, by the way, this number is famously known as the problem in particle physics because this number looks too tiny to be natural. But in any case, this is measured value. No question, this is measured value. And you want to compare this value to the electron mass, and you can easily find FestinaLente bound is fine. Okay, so but we can consider more carefully about the fact of this FestinaLente bound. Okay, this FestinaLente bound is okay because within the standard model, the Higgs expectation value is non-zero because the electron mass is given by the Higgs mechanism, and Yukawa coupling times vacuum expectation value gives you the mass. If vacuum expectation value is 0, your electron becomes 0. Then you cannot make your theory consistent with the Festina-Lente bound. Okay, so from the Festina-Lente bound, you can actually set the lower limit for the Higgs vacuum expectation value, that is 32 times pi times alpha times V over Yukawa over electron to the 1/4. Okay, so what you can learn? So electroweak symmetry should be broken to satisfy the Festina-Lente bound, right? And the authors of the paper also mentioned that the cosmological constant problem being slightly relieved because this bound gives you this, the cosmological constant to be less than 10 to the minus 90 m Planck square. So what you really want to solve is not from Planck to the 10 to the minus 122, but 10 to the minus 90 to 122. So it is slightly relieved, but I don't know if it is fair to say like that. Okay. So in the rest of the time, I want to consider the Higgs potential more carefully. So I briefly reviewed the Higgs in the standard model. This part is so elementary, so probably I can speed up my talk. So Higgs within the standard model is given by this charge. So singlet, doublet, and 1/2 hypercharge gives you the Higgs. Then your Higgs has the Goldstone G plus and G naught, and they are eaten by the gauge bosons, and you have vacuum expectation value and the physical Higgs. So this is the Higgs found at the LHC. And by insisting your theory is general, gauge invariant, and renormalizable, this is the unique form of the Higgs potential you can write down. And you can see this potential has only 2 free parameters, the quartic coupling lambda and the vacuum expectation value. And by expanding in unitary gauge, you can find the Higgs potential is given by the quartic term, that the coefficient of quartic term is lambda over 4. And cubic term, lambda V, and the mass term, lambda V square. Okay, they are correlated within the standard model. So to confirm this correlation is a very important step to confirm the standard model in the future. That's why we need future colliders. Okay, so we already know there are 2 roles of the standard model Higgs in the standard model: masses of elementary particles and electroweak symmetry breaking. They are experimentally confirmed. And more recently, we have realized that this same Higgs can play the role of the cosmological inflation. And I really hope this possibility can be checked in the future. Okay, so this plot, I really like this plot because this plot shows how beautifully the LHC confirm the role of the Higgs. Okay, so basically we want to see the linear relation between the masses of charged particle and masses of gauge boson and the Higgs vacuum expectation value. They are proportional to each other in the standard model. So you expect to see the linear line in the particle mass and the interaction, the plane of the mass and the interaction, and the LHC beautifully confirm from the top to the mu now. So at the moment, in this year, now we can tell Higgs to the mu is also consistent with the standard model. Okay, so it seems standard model Higgs really successful. And also by measuring the Higgs mass, we now know the actual value of the quartic coupling. Within the standard model, the Higgs self-coupling is given by mass square over 2V square. Mass is measured to be 125. Here, I show you many channels to measure the Higgs mass, and they find basically the same value, 125. Okay, and V is 246 within the standard model. And by calculating this, you can find the Higgs quartic coupling is 1/8, okay, within the standard model. So having this is the measured Higgs potential in the standard model. Okay, again, the first term and second term are predicted within the standard model. They have never been measured so far, so we really hope to measure this. Okay. So in the potential, we measure the curvature at the bottom of the potential. So we measure the mass, but we really have to measure the cubic term and quartic term to see the global form of the potential. Okay, and to do so, we are asking what's the shape of the Higgs potential at large field value, very separate from the electroweak vacuum. Okay, that's one thing we want to ask, and this can be partly understood if we consider the FestinaLente bound. Okay. Within the standard model, by the way, the cubic coupling runs because of the quantum corrections. Okay, this is one of diagrams describing the running of the Higgs self-coupling. So lambda is self-coupling and mu is the energy scale you want to measure. So by taking this, you define the beta function of self-coupling, and there are many diagrams, but the most importantly, you should notice the second diagram is the most important term, because okay, so this second term describes you the top quark contribution in quartic coupling. And because top quark is the heaviest particle in the standard model, it couples the Higgs the most strongly. So you can say that the coupling, the vortex is the most strong for the top quark. So you have the largest Yukawa coupling here. You have 4 vortices, so you got to the 4. And the top quark has 3 colors. So you have a 3 and you have 2 chiral states. So you have 2, so you end up with 6. And this top quark is fermion. So you really have to need the minus sign here. So -6 times u got to the 4 is the second diagram. And that dominates all over other terms. So you can easily see this whole thing is negative in the standard model. Okay, what does it mean? The Yukawa coupling, the Higgs self-coupling becomes weaker and weaker at higher energies. Okay, you already know the value at the electroweak scale, that is 1/8, as I told you, right? Then by turning on the beta function of the lambda in the standard model, you can predict the value at higher energy, higher value of the lambda. So the lambda becomes smaller and smaller at higher energies. And you can easily notice near the Planck scale, your lambda becomes tiny, tiny, small, and very close to 0. And also your beta function goes like this. And it is also small, near 0, near the Planck value. So this condition is found within the standard model with the LHC measurements. So I really think this is an important step to go beyond the standard model. So our Higgs in the standard model satisfies Higgs criticality conditions, lambda and lambda prime, both goes to be tiny, tiny, small near Planck scale or inflationary scale. Okay. Now, let me consider more general term for the Higgs potential. So we want to take the RG running of lambda, but also want to take the higher order operators like h to the 6, h to the 8, and so on and so forth to take the new physics effects. Okay. So we can also add cosmological constant term for the in here. So this term is constant and this term is from the standard model running, and these terms are from the new physics, then you can find the generic form of the potential given like here. I guess this is almost, this covers almost all possible cases. The first case gives you the case where the electroweak vacuum is the unique vacuum of our universe, okay? But we can also allow two double prime, 2 or 2 prime, because the lambda goes to almost 0 or even negative. And thanks to the higher order terms, you can make your potential turn like this and goes to a larger value at higher energies. And also you can allow this case 3, okay? So in a case 2 or case 3, you allow the electroweak vacuum, but also the other vacuum at UV scale, okay, very large scale of the Higgs, okay? So now I want to apply the Festina-Lente bound for those possible shape of the potential. That's what I want to do. The first, we already considered electroweak vacuum, right? So in the electroweak vacuum, with the measured value of cosmological constant, we already learned the Festina-Lente bound is fine. I told you a Festina-Lente bound gives you lambda should be less than 10 to the minus 90 and Planck square, and actual value is 10 to the minus 122, so it is okay. That's what we already have considered. And case 3, unfortunately, we cannot apply the Festina-Lente bound because here the vacuum energy is negative, so you cannot tell the universe is de Sitter. So here, basically, your vacuum is within the anti-de Sitter space, okay? So we cannot really tell the consistency for this case.
Sorry, one question.
Yes.
In this case, we are still sitting in the standard model vacuum, right? So
we are here right now. Yes.
So we are here. So this other vacuum exists, but the universe is not in this vacuum. So is this vacuum really relevant apart from that we have to make sure that we don't tunnel into this vacuum within too short time?
Yeah, very good question. So there have been several studies. I think the most important one is from Tokyo group. They really consider the tunneling of this vacuum to this vacuum and found the tunneling time is basically too large, so it never happens. Okay, so even well, in that case, we still say this is fine with the Festina-Lente bound. I just want to tell this may be okay from the perspective of stability of this vacuum. This is unstable, metastable, but this is fine. But theoretically, we want to tell if this is fine or not. But Festina-Lente bound cannot be applied for this case. That's what I want to say. Okay. Thank you. So now let me move on to the case 2. So I separate case 2 in 3 sub-cases. So the 2 and 2 prime have the vacuum like this. So you have a vacuum here or there. Okay. So here the vacuum is almost degenerate with the electroweak vacuum. This vacuum has slightly high energy compared to this energy. And double prime is the case when the potential has inflection point. So you change the slope like this, and you find this part can satisfy the slow roll condition. So you still apply the Festina-Lente bound. Of course, this case, universe is metastable. So you may try to apply the Festina-Lente bound. And also this case, right? And just to plug in the equation from the Festina-Lente bound, I can find this relation. So this is the m to the 4 over 8 pi times alpha. And within the standard model, the charged particle, the mass of charged particle is given by Yukawa coupling times vacuum expectation value. So this is replaced by Yukawa and vacuum expectation value. And this is the height of the potential within the standard model. So by just comparing this and that, you can find the lambda at VUV. VUV is the vacuum here, there. Should be less than Yukawa to the 4 over 8 pi times alpha. If you plugging in the standard model value at high scale, after taking the RG running effect, you can see this number is around 10 to the minus 22nd, meaning the Yukawa coupling becomes tiny, tiny, tiny small. Okay, so that means if you allow the second vacuum at UV scale, that vacuum should be nearly degenerate to the electroweak vacuum. Okay, you cannot allow very high the potential like this. Okay, so this height is limited by the Festina-Lente bound, and that limits the size of the effective coupling. Okay, so this is one thing we could learn from Festina-Lente bound for the UV vacuum. So by having the UV vacuum, degenerate vacuum, you can actually solve the vacuum expectation value and the cutoff scale when you allow the h to the 6th term. So you have two conditions, right? V is 0 and V prime is 0 at the degenerate vacuum. Then you can solve the equations like this. And by you already know how the standard model coupling runs within the by the top quark mass. So you can connect the top quark mass and other observables, the value of the Higgs and the vacuum expectation value and the cutoff scale. And depending on the mass of the top quark, you can tell what's the preferred number for those values. So for instance, if your top quark is 171.5, you allow the vacuum expectation value of the Higgs around 10 to the 14 GeV, right? This is one thing you could learn from the FestinaLente Bound. Interesting, right? Now let me move on to the final topic of my talk. So the topic is inflation. So of course, we know there could be other fields, other scalar fields. By allowing other scalar fields, we can now tell the height of the potential is given by the summation of the Higgs potential and the potential of other fields. Okay, it is almost hopeless to identify each potential of the other fields, but interestingly, we can tell the total sum of the potential is measured by the Hubble parameter during the inflation. Okay, because during the inflation Hubble parameter is given by the Hubble the Friedmann equation, and that sets you the relation between the total sum of the potential and the Hubble parameter. So now you can compare the Hubble parameter and the lightest, the mass of the lightest particle. Again, the lightest charged particle within the standard model is electron. So we want to compare the mass of electron and Hubble parameter. Okay, this is nice, right? Even you don't know each potential, you still know the total sum that is set by the Hubble parameter. So by setting up this FestinaLente bound, you can now read the field value of the Higgs during the inflation. And that is given by this nice equation, 96 pi alpha over Yukawa to the 4 to the 1/4 times root of m Planck and 8 Hubble. Okay. So by having this relation, you can now read the allowed consistent range of the Higgs value and the Hubble expansion rate during the inflation. And And also we want to set the reheating temperature higher than BBN temperature or electroweak temperature. We can find the consistency bound for the Hubble rate. So this lower part is not allowed if you set the reheating temperature is higher than BBN. And this line is newly obtained by FestinaLente Bound. So Hubble rate cannot be larger than this, should be larger than this combination. So you cannot go above this line, okay? So assuming the reheating temperature and FestinaLente Bound, the consistent value for the Hubble rate is here, okay? I terminate the value of the Higgs at the en blanc. So this is the allowed range for the Hubble rate and the Higgs expectation value. Interestingly, the Hubble, the Higgs field value of the Higgs should be larger than, say, for instance, 10 to the 4 if you allow the reheating temperature higher than BBN. If you want to allow the reheating temperature larger than electroweak temperature, then Higgs field value should be larger than 10 to the 8. Okay, what does it mean? If you allow the shape of the Higgs potential, your Higgs cannot stay at the electroweak vacuum during the inflation. So during the inflation, your Higgs field is away from the electroweak vacuum and universe evolves at that reason, okay? That's interesting. As you can link the Hubble rate to the tensor to scalar ratio in a simple inflationary model, you can set the limit on the tensor to scalar rate and the Higgs field value, okay? So that is given by 3 times 10 to the minus 15 and the alpha and AS and the Yukawa coupling and so on. So basically tiny small tensor to scalar ratio is expected if we take FestinaLente Bound very seriously, okay? So if in the future, some experiment can find larger value for the tensor to scalar ratio, we will re-examine the FestinaLente Bound, or we really have to modify our theory from the beginning, I think, okay? Finally, I want to comment on dark gauged U1. For the electron, we know the electron is stable because the electron is the lightest charged particle of under the U1 EM. We can think of same kind of mechanism to protect the stability of dark matter. So by assuming U1 dark gauge symmetry, and if some particle is the lightest of all, then because of the same, taking the same reason, your dark matter is stable, okay? In that case, you can apply FestinaLente Bound for dark matter, okay? So dark matter mass is said to be larger than this combination, vacuum expectation value. Then by plugging in what we know, the values what we know, you can find this should be larger than a certain value, that is 10 to the minus 3 electron volt, assuming alpha dark is same as the alpha ENM and Q is 1, okay? This number is roughly the neutrino mass. So if dark matter is protected by unbroken U1, that that should be larger than 10 to the minus 3 electron volt if we take FestinaLente Bound. Interestingly, this excludes FIMP. If this FIMP is protected by U1 dark gauge symmetry, then this is excluded. This number is too small. And however, we also have to take the dark radiation part of from this U1 dark. So more study is needed in this particular case. Okay. Let me now conclude. So Festina-Lente bound is found from the black hole decay in digital vacuum. And you can memorize this formula, right? And taking RG running effect, we find that the UV vacuum should be very closely degenerate with electroweak vacuum, if it exists. Taking the potential effect from other scalars, we find the Higgs cannot stay at the electroweak vacuum during inflation. And the small value for the tensor to scalar ratio is expected. And finally, if dark matter is U1D protected, and that mass should be larger than neutrino mass. Okay, that's all. Thank you very much.
Very much. Any questions or comment?
Can I have a question?
Sure.
You said that after during inflation, so Higgs is not in the electroweak vacuum. Then I mean, now Higgs is the electroweak vacuum, right? So after the inflation, your expect is that I mean the Higgs classically climb up the hill, or there occurs the tunneling effect to our I mean electroweak vacuum. Which one?
Yeah, I think both are allowed. Because we don't know the other fields, we cannot tell what's the case. In any case, whatever the inflaton field behave during the inflation, we can just learn the Higgs field value should be away from the electroweak vacuum value. So both are allowed. Maybe Higgs potential goes up, and during the inflation, our Higgs is really stay up the hill or somewhere, or even you allow the negative value of the Higgs potential by help, but you still have a largest contribution from the other scalar fields. That's also allowed. So you can go downhill. So both are allowed.
So that after inflation, then I mean, can we calculate the decay rates from the VUV to V electroweak? And how big is
that's
that?
an interesting question. But important thing is the Festina-Lente bound cannot be applied fastly for the fastly moving potential. So even when we can discuss the vacuum or the stable vacuum, unstable vacuum, metastable vacuum, and the slowly rolling stage of the Higgs potential, we cannot really tell how it transit from that UV vacuum to the electroweak vacuum, unless the transit is also very, very slow. At the moment, we cannot tell if that transition is really, really slow. So we cannot tell how fastly it transit from the other vacuum. But that would be interesting question actually, and having the model for the other fields, maybe we can more discuss about the transition for the Higgs field. Model independently, we cannot tell.
I see. Okay, thank you. Can I have one more very stupid question? So, I mean, every time I hear about the FestinaLente bound, I wonder how robust FestinaLente bound is.
Yeah.
So
yeah, I as I described in the earlier part of my talk, FestinaLente bound is from the largest of potential the black hole. So question is, if we do have such kind of very large black hole, the size of black hole is same as the universe itself. yeah, that's another question, right? In reality, maybe it's not possible, actually. However, we can still ask consistency of the theory. If you allow this charged particle and this vacuum expectation value, then you solve the equations and you can find the black holes and you can consider black hole mechanism and see if this theory is consistent from the beginning to the end or not. Right? This is theoretical question. And this Festina-Lente bound is more about consistency of a theoretical setup of our universe with unbroken U1.
But I mean, in Festina-Lente bound,
Mhm.
so you forbid every particle
Mhm.
whose mass is smaller than charge.
That's right.
But I mean, so if there is, I think at least one, the mass is bigger than charge, then maybe that channel dominates. Then it, the situation will be consistently. I mean, we can make decays of the black holes, right?
I think that's the question about quantum process. So
Yeah.
we take Hawking radiation as a part of the quantum process. So even though some particle is dominating over all other particles, we still allow the probability, non-zero probability for other processes by other particles. Yeah, so again, from the consistency, Festina-Lente bound seems to be pretty robust. Yeah, that's what I can tell.
So, for example, in weak gravity conjecture, we only need one particle or the
Right.
fields.
Yeah,
right?
But here,
yeah.
every particle should satisfy this condition. So that's difference. Yeah.
So I mean, to climb that, I mean, we need more, how to say, more theoretically, like the strong, I mean, kind of symmetry or other things, not this phenomenological thought experiments, I think.
Yeah,
So,
yeah, indeed, there are other works within the string theory construction of models, and they have checked Festina-Lente bound from their construction of stringy models. So, yeah, today I just told you a simpler version of Festina-Lente, the derivation of Festina-Lente bound, but there have been several other works as well.
okay, I see.
But again, this is not proved conjecture, right? This is still conjecture, just like weak gravity conjecture by itself. Yeah.
Okay, thank you.
Thank you.
I have one question concerning the assumptions you make on the Higgs potential, because so in order to write down this potential, you were writing down basically dimension 6 and dimension 8 operators. So do you also allow for other dimension 6 and 8 operators?
Well, I tried to write down the effective potential in this way. Yeah, so yeah, we are sure we have dark energy and the standard model part of the running coupling.
Yes.
And then I regard the other terms are from the new physics. I didn't.
No, I'm asking because one part which is crucial in this bound, as far as I understand, is that you can run or that you can extrapolate the Yukawa coupling to high scales. So if anything is modifying the relation between the Yukawa coupling and the Higgs mass, then this can have an implicit effect on the mass bound of the lightest particle.
So Within the standard model, we simply assume mass for the elementary particles are given by the Higgs mechanism.
Yes,
Yeah,
but
that's
if I
how
write
we-
down dimension 6 operators, I can write down a TT bar H cube term.
Ah, I see.
And
Mass
this is
is from higher
modifying
order
this.
terms.
Okay.
Mass
Yeah.
is from the higher order terms. Yeah, we didn't take that possibility in our analysis. But they don't really contribute the shape of the Higgs itself, right? Shape of the Higgs.
No. They have nothing to do with the Higgs potential.
Yeah, but the mass.
The only thing they could do is influence the
mass.
relation between the Yukawa coupling and the mass.
Yeah.
In practice, I mean, nowadays those corrections have to be pretty small.
Yeah.
But if it could do something at an earlier stage if you are at a different,
that's actually correct. Yeah,
different vacuum.
right. Very interesting. Yeah, we should discuss more.
Yeah,
right.
and I also wanted to ask, all those assumptions or all those calculations are done in the vacuum at 0 temperature. Now, in principle, if you are at finite temperature, you also could get a contribution to the effective masses of the so for the Higgs potential as well as for the top from finite temperature effects. Do you know whether anybody looked at? So first of all, is this relevant? I.e., would this modify, or because I know too little about the cosmology to know whether the phases you are discussing are basically at 0 temperature or whether finite temperature could play a role? And do you know whether anybody looked into finite temperature, if it is relevant anywhere?
Okay, first, in my case, finite temperature effects are not important at all because in our vacuum, we know temperature is low. During the inflation, we know temperature should be tiny, small.
Okay.
So both are 0. So we don't need to take that effect. And also, I doubt if there can be any circumstance where the temperature effect can be significant, and also, but still, the FestinaLente bound is applicable. When temperature is high enough, and you modify the shape of the potential, you probably make the running of the Higgs at that phase can be not slow. I mean, yeah, depending on the shape of the potential. So in that case, the slower parameter with the finite temperature can be, I think, easily order 1, but we need to check. Yeah. That's also interesting comment.
No, because I was thinking maybe a final point from my side, because you have models where you have restoration of SU2 cross U1 symmetry at finite temperature.
Yeah.
Which in that phase, you in principle would have a restored U1Y symmetry under which the neutrino is charged. So I am thinking whether you could use this bound in order to derive some sort of lower bound on the mass of the neutrino.
Yeah.
Under the assumption that you have symmetry restoration anywhere.
Yeah. So when U1 hypercharge is restored, yeah, certainly the lightest particle is the neutrino.
Yeah.
So we can compare the neutrino mass and the FestinaLente bound. Yeah. Yeah, I haven't thought it carefully yet. So maybe we can discuss more.
Absolutely.
Okay. Yeah.
Thanks a lot.
Thank you.
Any other questions or comment? I have question on page 35.
35. Okay. Yeah.
Could you a little bit more explain about the last sentence? The mix when the dark gauge mix with
Yeah, right. So to discuss dark gauge U1, I assumed dark matter is protected by this dark U1. In that case, and also I want to protect the stability, this U1 should be unbroken. So we really have dark radiation, massless dark radiation. And the question is how this dark radiation shows up in our experiments. And that depends on how it mixes with our photon. For instance, you allow kinetic mixing of dark radiation and our photon, definitely the effect can be seen some of our experiments. That's what I wanted to say. I didn't really work out this possibility yet. So yeah, this can be another topic we can discuss more. Okay.
So can I make one comment on this slide?
Sure.
So yeah, I think this bound is interesting, but the bound is around 10⁻³ electron volt for this chosen value of alpha and QD.
Yes.
And in fact, I think for such a light dark matter being fermionic or bosonic, they will have a very long lifetime kinematically. So I think this bound will be useful if this bound were larger than order of tens of kilo electron volt for fermion and the order of electron volt for the boson. But of course, this argument depend on the dimension 5 operator that make the dark matter decay. The question is how large is the coefficient of this dimension 5 operator when you assume the new physics scale is m Planck. So this if you depending on you whether you assume order 1 coupling for this dimension 5 operator, or for some reason you can have a very suppressed coupling for the this dimension 5 operator. I don't think there is a kind of semi-rigorous argument about the size of this dimension 5 operator that induce the dark matter decay. But anyway, I think roughly speaking, for 10⁻22 electron volt film, for example, they will be they will not be stable, but their lifetime will be long enough to be a dark matter candidate, because kinematically their lifetime will be very, very long.
Yeah, thank you for the comment. Yeah, here I just simply assumed dark matter stability, absolute stability is guaranteed by the gauge U1.
Yeah.
Kinematic.
Yeah, I think the first part of this equation is interesting, very interesting relation, I think. Yes.
Okay, yeah. Thank you.
Any other questions or comment? Maybe a lot of questions. So thank you very much.
Thanks a lot. Thank you. Yeah.
Thank you very much.
Thank you.
You gave 2 talks in
Yeah.
Jeju. But the audience is different and you get different questions and so on.
Right. Yeah, it's very nice. Yeah. Yeah. Let's discuss more. I think there should be other other situations to apply this facility. Yeah. Thank you. See you later.